Exactly.
I forgot yesterday.
Let's talk about what's going to be on the test. I will tell you, the vast majority of the tests are going to be calculations using either the ideal gas law or the combined gas law. So we'll kind of go through these things and talk about them, because there will be some conceptual questions on the test as well. Yeah, we will. Let's do this first. But yeah, most of the questions are going to be just calculations, much like the first two worksheets that we worked on. So number one says you should be able to describe the basic motion of gas particles based on the kinetic theory of matter and how it explains gas pressure. This is really a throwback to last chapter. Just don't forget that molecules are bouncing all over. They're hitting the sides of the container and each other and anything that's in the container. They're basically hitting everything that they bounce into, and that's what causes gas pressure. Okay? But we should be able to use that gas particle motion to explain effusion and diffusion. So as those molecules are bouncing into each other, they're bouncing all over the place, and over time, that's just going to spread them out. That's diffusion. So if I spray some sort of gas or let a gas out here in the front of the room, over time, as those molecules bounce into air molecules around them and off the board and off of us, they're going to just spread out until they're kind of evenly spread out throughout the room. So that's diffusion. Effusion is much the same thing, except in a container, those molecules, as they're bumping into things, every once in a while they'll find their way through the container. They'll find their way through a pore or a hole in the side of the container and escape. And that's effusion. Yes. Now some containers don't have pores small enough for those gas molecules to be able to escape. So this soda bottle, if it's sealed up pretty good, carbon dioxide in it, it's in the soda that gives it the carbonation, really doesn't have anywhere to go. There's no pores to escape through. But something like a balloon, there is, which is a porous material. There's enough holes that some of those molecules can get free. Sheetrock, absolutely. Gas molecules move through sheetrock all the time. That's why just having sheetrock on the ceiling isn't good enough to insulate your house. You blow in the insulation or put in those bats and everything to slow the rate of effusion, slow the rate of movement of the air molecules, the hotter air molecules through that material. That's the whole point of insulation, really. It's just to trap the air molecules and make it so they don't move as quick. But, I mean, you wouldn't necessarily want a complete vapor barrier either, because there's all sorts of things that can happen there.
So what about brick?
Oh, brick's very porous. Yeah, brick lets the molecules through all the time.
So brick does actually.
Yeah, a brick wall, like even a concrete wall, has a very small R value. I mean, it's about the same as a...
If you have a baseball on one side, it's a long.
Well, no. You're not going to feel it.
Statistically, you are sending more air molecules.
That is true, but it's you're not going to feel the difference. But
Yeah, it's like air conditioning puts it up against the wall.
Yeah. Just over time, air molecules are able to move through them. Okay, number 3, list different properties of gases and describe how they affect the pressure of a gas. So this is things like number, molecules, temperature, volume.
So really, you're building this, or what you have the people that build the most
There's lots of reasons for that, but you're gonna have to put it in insulation. True. But it lets it through too. Nowadays, a lot of people use those insulated concrete forms. So they're, they got insulation built in. Okay, moving on. The number of molecules, when we're talking about a sample of a gas, like in this soda bottle, the number of molecules is going to be directly related to the pressure. If we add more molecules, if I put more air in here using an air compressor, it's going to increase the pressure. Okay? Temperature, also directly related to the pressure. If I increase the temperature, if I warm this thing up, the air molecules are going to move faster, it's going to increase the pressure. True. Volume is the odd man out. It's an inverse relationship. If I make this bottle bigger and I keep the same amount of air inside there, the air pressure is going to go down. If I want to increase the air pressure, I have to make the bottle smaller. I have to decrease the volume. Like squeezing. That'll increase the pressure. Squeeze on that hard enough, the top will pop off. That could happen too. That's true. Okay, so you should just be able to talk about how each of these would affect the pressure of a gas. If I add some molecules, or if I take some molecules away, you should be able to explain what's going to happen. Okay, but that all goes into number 4, using the combined gas law. Just remember, the combined gas law is P1 times V1 over T1 equals P2 times V2 over T2. You will have that equation on your constant sheet tomorrow. Friday, sorry. And remember, we can use this for any problem that talks about a gas changing properties. So we have a sample of gas that is changing pressures, changing volumes, changing temperatures. But if something is changing, you're going to want to use the combined gas law. Right? In some situations, in some problems, maybe all 3 things are changing in some way. But there will be some problems where it may say the volume is constant. And if you remember, if the volume is constant, that means both of these numbers should be the same. And so it really doesn't matter what numbers you put in as long as they're the same. Your calculations will work out right. But if you're going to put the same number in each case, make it easy, put 1 there. That's another way to think about it. You can remove that from the equation. That's another way to go about it. That's true. I don't know. It's 6 of one, half dozen of the other. But, I mean, technically, if the volume's staying the same, the point is both those numbers are the same, and we can cancel them out on either side of 1. Okay? The ideal gas law, this is the one that says P times V equals N times R times T. And we use the ideal gas law to calculate a specific measurement, so say the pressure, based on other specific measurements like the temperature and the volume and the number of molecules. So the ideal gas law is used when we just go, hey, like you guys did in the lab the other day, how many molecules are in this balloon? Or hey, based on this information, what would be the volume that this gas would take up? Okay, so we use the combined gas law for changing gases. This is for a single situation. That's probably the biggest thing you have to keep track of. Okay. It was just a really long one with a break in here. There we go. Okay. The other thing, remember, with the ideal gas law, you have to be careful about which gas constant that you're using. I will have both gas constants on the constant sheet tomorrow. Remember, if you're using atmospheres, this one's probably the easiest. If you're using pascals, don't forget this is in kilopascals, so you have to convert. You have to divide by 1,000 to get it into kilopascals before you put this number into the equation. I will also put the conversion between atmospheres and pascals on the constant sheet if you would rather use that. Some people find it easier just to take the pascals and convert into atmospheres and then use this one all the time. It's completely up to you. I don't care how you do. But you will have some problems that the pressure is given in atmospheres, some problems where it's given in pascals. So you got to be able to use it both ways. Yeah, I just said that. Literally. So that's perfectly fine. If you would rather just convert from pascals to atmospheres and only use that one gas constant, that's perfectly acceptable. That's no problem. Doesn't matter which way you do it. And number 6, we didn't really talk about. I'm not going to put a whole lot on the test, but the point is that the ideal gas law doesn't really work very well for gases that are really cold because of some different things that happen when gases get really cold. But we'll just kind of skip over that. So I decided to skip over it when we were talking about it. Number 7, though, you should be able to describe Dalton's law of partial pressures.
1 plus 2 plus 3 equals.
Pretty simple. Remember, the total pressure in a sample of gas is going to be equal to the sum of all the pressures of each of the gases. So kind of like I said yesterday, if Isaac and Riley and this guy, Luke, all go push on that door, the total amount of force that they're putting on that door would be equal to each of the forces, the sum of each of the forces they're pushing with. It's the same thing with gases. In here, there's nitrogen, there's carbon dioxide, there's oxygen. Each of those gases provides a pressure. The total pressure has to be that, the sum of all of them. Thank you, Luke. Okay, so that's Dalton's law. Not too hard. Graham's law of diffusion basically just states things with lower molar masses are going to effuse faster. They're smaller, they're able to find their way through the holes easier. But we also have an equation for that. That goes into number 9 here. Remember, that's that the diffusion rate is equal to 1 over the square root of the molar mass. That equation also will be on the sheet tomorrow. We just did those types of problems. But remember there, you want to compare and say, this one is this many times faster than this one. That's pretty much all there is to it. If you can do combined gas law and ideal gas law, should be, I mean, that's 80% of the test. The others are just filling in the gaps with some of this knowledge. And there will be a couple diffusion rate calculations. Maybe 1, maybe 2, I don't remember. Okay, any questions?